Molecular geometry, sp hybrid orbitals. In this tutorial, we will be talking about why does beryllium form a covalent bond, sp hybridization of beryllium, beryllium chloride example, sp hybridization of carbon, hydrogen cyanide example, sp hybridization of carbon, carbon dioxide example, and some practice questions at the end. Why does beryllium form a covalent bond? Key points to understand beryllium. Beryllium is a group 2 metal, as we can see in this image down here. It is an electron deficient element. In other words, to be stable, it does not need a full octet of electrons. So this is very similar to what we see with boron. It does have a high electronegativity compared to surrounding metals. So beryllium is 1.6, magnesium is 1.3, lithium is 1, and sodium is 0.9. We can see that beryllium has high electronegativity values compared to surrounding metals from group 1 and group 2. This means that beryllium has the ability to attract neighboring electrons to itself more strongly than other metals. In order for an ionic bond to form, metals need to lose electrons to form positive ions. Beryllium is just too electronegative for that. So let's look at our example, beryllium dichloride. And I put the prefix di here on purpose because BCl2 can be represented as beryllium dichloride or beryllium chloride, so just be prepared for both. Consider the bonding in a molecule of beryllium dichloride, BeCl2. Below we see the orbital diagram for the standard atomic orbitals in a beryllium atom. So the electron configuration for beryllium is 1s2, 2s2. And if we focus just on the second principal energy level, we see the 2 electrons in the 2s orbital, one up and one down. So if we were to do a beryllium Lewis symbol, we could represent this with a capital B and then 2 electrons at the top, representing the 2 electrons in the 2s orbital. In the ground state electron configuration for a beryllium atom, there are no unpaired electrons available to bond with the 2 chlorine atoms. The linear geometry in BeCl2 can be explained by the hybridization of one 2s orbital and one 2p orbital on the central beryllium atom. The 2 remaining 2p orbitals, 2px and 2pz, remain unhybridized. So the mixing of the 1 2s and the 1 2p orbitals gives us the 2 sp hybrid orbitals, 1 2, and then we have unhybridized p orbitals left open. So the beryllium Lewis symbol could now look something like this. So 1 dot at the top, 1 dot at the side. Beryllium's 2 valence electrons occupy the 2 sp hybrid orbitals with parallel spins according to Hund's rule. The 2 sp hybrid orbitals all have the same energy. In other words, they're degenerate. A central atom with sp hybridization has 2 sp hybrid orbitals, 2 electron domains, with a linear electron geometry with bond angles of approximately 180 degrees. So we have 2 electron domains here, one bond and another bond. So our electron domain is equal to 2. So think of that as 2 letters. So our hybridization will be sp. 2 electron domains can be observed as one triple bond and one single bond. So for example, the central carbon atom in hydrogen cyanide, HCN, is sp hybridized. So there are 2 electron domains here off the central atom of carbon, one here and one here. So electron domains is equal to 2. Think 2 letters, sp. 2 electron domains can be observed as 2 double bonds. So another example, the central carbon atom in carbon dioxide is sp hybridized. One electron domain here, another electron domain right there. So electron domains equal 2. You think 2 letters, sp. Let's do a practice problem. Give the hybridization for the carbon in HCCH, otherwise known as ethine. So we could pick either one of these carbons to look at. So I'm going to look at this carbon right here. Here's one electron domain. Here's a second electron domain. So the electron domains equals 2. I think 2 letters. So my answer has to be C, sp hybridization. Let's look at another example. A molecule containing a central atom with sp hybridization has a blank electron geometry. So with tetrahedral, we know that in a tetrahedral electron geometry, the electron domains will equal to 4. If the electron domains equal to 4, think 4 letters. That's sp3 hybridization. With trigonal planar, there are 3 electron domains, so think 3 letters, sp2. But for linear, the electron domains in the linear geometry will be 2, think 2 letters, sp. So the correct answer here is C, linear. So what did you learn? We answered the question, why does beryllium form a covalent bond? We talked about the hybridization of beryllium and beryllium chloride, the hybridization of carbon and hydrogen cyanide, the hybridization of carbon and carbon dioxide, and then we did a few quick practice problems at the end. Need more help? Feel free to contact me. Have a great day.